So far we have talked about the way to classify matter, or sorry, how to describe or define matter. We've talked about the states of matter, changing between the states of matter, and now we're going to take a look at classification of matter. And to start off with, we are going to look at the pure substance. So this is anything that has a definite and fixed composition. Because of this definite and fixed composition, that means it's always made up of the same number of atoms, same type of atoms, etc. There are characteristic physical and chemical properties that can identify them. So we've talked about chemical and physical properties, the fact that those characteristics can be used to characterize a substance. Pure substances have set chemical and physical properties that we've talked about. These cannot be separated by physical methods. So there's actually going to be two categories of pure substances. Those are elements and compounds, and we'll define those momentarily. But elements and compounds, they cannot be broken down by physical methods, and we'll talk about what I mean by physical methods later on. But those two things cannot be broken down any further. So let's take a closer look at elements and compounds. So first off, we'll look at the elements, and the elements should be pretty straightforward because you can find them on the periodic table. So if it's an element, it's found on the periodic table. They can exist as atoms or molecules, and the thing with the molecules that are considered elements is they only contain one type of atom. So you might see something with a formula. Actually, we'll look at this later on in this slide, but if I have something like Br and there's a little 2 next to it, this little 2 tells me there's 2 of this type of Br atom. That's a bromine atom, but it's only one type of atom, so that would make this classified as an element. So just to define what an atom is, in case you don't know, it's the smallest unit of matter that retains a certain identity, and we will actually study the structure of the atom, protons, neutrons, electrons, all that good stuff in Unit 3. Next, a molecule, in case you don't know what that is, that's 2 or more atoms that are chemically bonded, so that means that they are sharing electrons, and those 2 atoms or more atoms are being held together by that bond. So elements cannot be broken down into simpler substances, and we had said that any pure substance can't be broken down by physical means. Elements can't be broken down by any means, whether it be physical or chemical. There are 7 diatomic elements. So when I mentioned the fact that elements can exist as atoms or molecules, there are 7 elements that naturally, when they're in their elemental form, actually exist in pairs, and that's what diatomic means. So di means 2, and atomic is referring to atoms. So these elements, so bromine, iodine, nitrogen, fluorine, hydrogen, oxygen, fluorine, those 3. Now I put them in this order because it spells Brinkelhoff, which isn't actually a real word that means anything, but it kind of sounds like a word, so that can maybe help you remember which 7 elements are the diatomics. And you will need to know this. We're mentioning it now. Later on, when it comes to writing formulas, you will notice us utilizing the knowledge that these are diatomic much more. But for now, we should memorize that these are the diatomic elements. And another way to remember this is if you look at the periodic table. Notice hydrogen's all the way over here by itself. But the other diatomic elements that I mentioned, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those actually form a 7 on the periodic table. So we can see where the mouse is tracing. It actually forms a 7. So again, you can locate those 7 diatomic elements. Once you find one of them, you can kind of go across and down. And then, of course, little hydrogen's all the way over here by itself. Okay, moving on. Another thing we should know about elements is a vocabulary word, which is allotropes. And I guess if you want to pronounce it allotropes, you're British saying hello to the tropes, I don't know. These are different forms of an element with different numbers of atoms and different properties. So for example, oxygen, which is one of our diatomic elements, normally exists as O2, as you can see right here. It's actually another form of it. So this is also a gas. So it happens to be allotropes are containing the same atoms, same types of elemental atoms. However, they're combined in a different amount. So this molecule of ozone actually has 3 oxygens joined together. Very different properties from the oxygen that we breathe, that we require for living. Ozone is actually very dangerous to be breathing in. Exists up in the ozone layer, but also can sometimes be formed as a result of pollution and so forth. So Allotropes is another vocabulary word that we should be familiar with that refers to elements. And again, it's different forms of an element with different numbers of atoms and therefore different numbers of properties, different properties. Here are some examples to show you what allotropes. So like carbon has allotropes also besides oxygen. So this is graphite. So you find that in your pencil lead. And there's diamond. And obviously those two substances, very different in value, especially in hardness. We know that pencil lead breaks all the time. Diamonds are supposed to be, or are the hardest, strongest substance on Earth. So again, both just made of carbon. They're both considered elements. However, because there's two different versions, and it has to do with how the carbon atoms are hooked together, but they're two different versions of the same element, and so that's what an allotrope is. For the compounds under pure substances, these are made up of elements in a fixed proportion. So they've got a fixed number of each type of atom. It's unchanging. And again, we look at the chemical formula, unlike what we saw with the Br2 or the O2, which were considered elements, these are going to have more than one type of element. So you're going to see, a couple of different element symbols, and they're going to be written with no spaces between them. That's how we know that it's a compound. Pure substances, compounds can be broken down into the elements through chemical reactions. So we said that elements cannot be broken down into simpler substances even by chemical means. Compounds can be broken down by chemical reactions, and one of the chemical reactions that can do this is called electrolysis. And probably some of us have heard of electrolysis on hair removal commercials. This is a little bit different. It's using an electric current being applied to the compound, and it decomposes it into its elements. And I'll show you an example of this in class. And the compound is going to have different properties from the elements making them up. So an example of this is sodium chloride. If you look at the properties of sodium independently, sodium as an element is a soft silvery metal. I can show you an example of this in class. And it's very reactive with water. It looks different than, we know sodium chloride is table salt. We know it's white, has a characteristic salty flavor, dissolves in water. Sodium as an element, very different properties. So when the elements are a part of a compound, they have different properties. Same thing with chlorine. In table salt, as sodium chloride, it again makes up the compound sodium chloride, has the properties of salt, but chlorine, again, that's one of the diatomics. We'd see it in its elemental form as Cl2. That is actually a toxic yellowish greenish gas, very, very dangerous to breathe. So again, very different properties, even though it's containing the same element. So a compound is a fixed proportion of atoms that are chemically bonded together. Okay, we will talk about this in the next unit, law of definite proportions, also may be referred to as the law of constant composition. And this just says a given compound always contains the same fixed ratio of elements. And this is the case that it's made up of the same composition by mass. So like if we looked at the mass percents, that would be constant. And also, as it turns out, that has to do with the fact that the numbers of atoms are constant as well. And if I have two different compounds, they both have to have different compositions. So notice the example here. We know carbon monoxide is, hopefully we know carbon monoxide is dangerous to breathe. People can die from carbon monoxide poisoning. Carbon dioxide, though, however, very different properties. It's still a gas, much like carbon monoxide, but it's in the air around us. We're breathing it out. It's not harmful, at least in small quantities. Because it has different properties, we know that it's a different compound, and as it turns out, it's a different compound because it does have a different number of oxygens making up the molecule. Okay, so besides pure substances, we've got elements and compounds. For mixtures, a mixture is something that contains two or more pure substances that are physically combined. So if I have elements and compounds and I put them together in a container, if I put them together and they don't react with each other, I have made a mixture. And the mixture retains the properties of the mixture components. So for example, if I make salt water, the salt water, it still looks like water, kind of, but it has the salty taste characteristic of the salt. So again, we can still distinguish the characteristics of the original mixture components when we make a mixture. they can occur in varying proportions. So unlike pure substances, I know that I can have salt water that's very salty. I could put a teaspoon of salt into a cup of water, and it would be salt water. Or I could put, a half cup of salt into a cup of water, and that would also be salt water, but it would be much saltier. So there's varying proportions for mixtures. They don't have fixed proportions like compounds do. These can be separated by physical methods, and we'll talk about those in class, but it does not require a chemical reaction like we saw with compounds and electrolysis to break these things apart. Since they've just been mixed together in a container, they can also be physically extracted and separated from one another. And our two types of mixtures will be homogeneous and heterogeneous, and I think most of us have seen these two types of compounds defined before, or sorry, two types of mixtures defined before, but we'll take a closer look at those next. All right, so homogeneous mixture. So the prefix homo means same. So again, we're looking for a fixed uniform composition. This in chemistry is also called a solution. So we work with solutions a lot. You should know what a solution is. A solution is the same thing as a homogeneous mixture. That's very important. It appears to be all one phase, even under a microscope. So the particles of the components of the mixture are so similar in size that even under a microscope, they appear to be uniform, and that's an important differentiating characteristic with a homogeneous mixture. They cannot be filtered. So if I were to run this obviously is apple juice over here as our example. If I were to run this through a filter, like a coffee filter, for example, you would not see the appley goodness being filtered out because the particles are too similar in size to separate them out via that method. Components will not settle out. So I could leave this apple juice sitting here all day long and we're not going to see bigger particles settling down to the bottom. And that's another characteristic of homogeneous. If it's truly homogeneous, the particles all are so similar in size that they're all going to stay mixed and suspended. And some other examples are an alloy. So usually when we think of homogeneous mixture solutions, we're thinking of a lot of times liquids, but you can actually have gaseous mixtures, you can have solid mixtures. An alloy is an example of a solid mixture. It's a homogeneous mixture of two or more metals. Some examples are brass, bronze, steel. So a lot of us have stainless steel cabinets at home, not cabinets, appliances. We might have seen, bronze or brass fixtures like, on doorknobs or on furniture. So those are mixtures of metals. They were melted down, mixed together, and then cooled down. And so those are also considered homogeneous mixtures because we would not be able to differentiate the pieces just by visually inspecting it. Next type of mixture, we've got heterogeneous mixtures, and different phases can be detected. So we see the picture of the granite. So a lot of people have granite countertops these days. You have also seen like concrete. It's a stone, has little pebbles and things in it, sand. You can detect the different pieces. They can be filtered. Now, I'm not saying that this piece of granite can be filtered. What I'm saying is if it's a liquid mixed with a solid, that can be filtered, or it can be physically separated some other way. Like by picking out pieces. Like if I have raisins in cereal and I pick those out, that's a heterogeneous mixture. I can see the raisins, I can pick them out. Particles may settle out when left standing. So let's say something temporarily looks homogeneous because you've shaken it all up. If those particles end up settling out, what that means is they're way too big to actually be a true solution, to stay suspended, to stay dissolved, and so they settle out. So that would be a characteristic that would tell us something's heterogeneous versus something that is truly homogeneous. Different parts can be seen under a microscope. So we're not going to be actually looking at anything under a microscope in here, but if we were to look at a heterogeneous mixture under a microscope, you would be able to see the little chunks or pieces of something that that you wouldn't see in a homogeneous, because they're differently sized particles, and that's why we're able to see the different phases, because it's heterogeneous. There are different phases. Okay, so here's a little flow chart to help us to classify matter a little bit more easily, and we're going to do some practice with this on the next slide. So if we have matter, well, first of all, we classify it. Is it matter in the first place? So does it take up space? Does it have a mass? If the answer is yes, then it's matter. So then we're looking at, can it be physically separated? So can I filter it? Can I boil it? Can I separate out the two pieces If the answer is yes, it's a mixture. If the answer is no, then it's a pure substance. If I can chemically decompose it, so if I try electrolysis and I can break it down further and there's a reaction, then yes, it's a compound. If no, I can't separate any further, then it's an element. Going back to the mixture side, if I determine it's a mixture, if the composition is uniform, so I'm looking at it and I see that it all appears the same, that would be a homogeneous mixture or a solution, and if not, then that is heterogeneous. So let's take some practice at identifying mixtures and pure substances, and so see if you can figure out which of these is an element or a compound or homogeneous or heterogeneous mixture. So first think about, is it a mixture, is it a pure substance? Then think about if it's a mixture, is it homogeneous or heterogeneous? If it's a compound, sorry, if it's a pure substance, is it an element or a compound? So take a minute and think about that.